Hey everyone, this video serves as an introduction to Actor-Critic and Proximal Policy Optimization. These are two algorithms that build upon Reinforce. If you guys remember the first video in the series, we went over Reinforce, which was a policy grading algorithm for reinforcement learning, and we applied it to Cartpole, which is a very simple environment in OpenAI Gymnasium. But the purpose of that algorithm was to introduce policy grading algorithms and slowly build our way towards a chain and a timeline of modern large language model post-training techniques. And one of the more revolutionary techniques is using PPO in RLHF. So this little arc of videos, for the next couple of videos, we're going to be going over PPO and then implementing it in an RLHF environment. But before that, we have to understand the important algorithms that came before PPO. And we have to understand PPO just in the context of reinforcement learning, right? The first thing that came along after Reinforce, or what I deem important in this timeline, is Actor-Critic models. And I'm going to go over this right now. But first, we have to understand why. We have to understand the pitfalls of Reinforce and why Reinforce isn't used that much in RLHF. Now, truth is, actually, there have been different research papers on using Reinforce, and they've come out pretty good. So it's not too bad, but we have to understand the downfalls of it and why things like Actor-Critic and why things like PPO came to be, and then why they are better for large language model post-training. And so I'm going to share my screen so that we can just talk about Reinforce. I'm going to show the implementation that we did. Now, the implementation that we did is right here for Reinforce. And I want to pinpoint one of the problems with this algorithm. And the problem lies here, in which we calculate the returns after each episode. So look, we have to loop through a whole episode. If you guys remember, an episode is basically a whole, like the start to finish of an environment. In this case, in Cartpole, it ends when the thing falls or when you reach 500 time steps. And so we use that episode to collect data, which is basically all we do here, right? We make an action with our model, and then we see what that action ended up in us getting rewarded. And we append that to some list. And then from there, we approximate, or we calculate a return. The return would be like the total reward that we get throughout the whole episode. And our goal is to maximize this return. But the problem with that is, as you can see, just blatant inefficiencies in having to run a whole episode and relying on the raw return, which leads to like two problems. One, obviously, the inefficiency of going through a whole episode to collect the data. Obviously, in this case, Cartpole is very simple, but in a more complex environment, that takes a lot of resources. And another thing is just the high variance of a system like this. What I mean by that is the return, we kind of collect the whole return after the episode, right? What that means is, what that means is that we are grading, or we are evaluating an action of a policy model throughout the whole return that the episode produces. Let me tighten up the wording there. What that basically means is that a single action, depending on the return, whether it's positive or a good return or a bad return, that action basically gets all the credit for that return. So an action in step 3 depending on the return, gets the whole credit for that action, for the results of the return. And you can think about how this is a flawed way to analyze this, because obviously a step done or an action done in step 3, just because the total reward at step 500 was positive and really good, that doesn't necessarily mean that the action taken at step 3 was the best one or was a good one for that matter. That could have been later stabilized, like in step 200 and things like that. And so this leads to high variance, in which we don't necessarily know to the best of our ability what action directly led to the greatest consequences or to the greatest rewards. So we have to find a way to better approximate the effect of an action on the reward that it gains from the environment. And so this kind of leads straight into what PPO is. I'm going to stop sharing. I'm going to start sharing here. And so Actor-Critic directly challenges this in a 2-model format. So Actor-Critic, we have the policy model, which is what we call the actor. So you could think of this one as the policy. But like I said, obviously this is the one that generates an action, right? Or outputs like a distribution over an action, like an action space over actions. This stays the same, but now we introduce another model called the critic model. Now this critic estimates a value. Now, what do we mean by a value? This basically means, given this state that we're currently in, right? So given state, how good is it? Which outputs singular scalar that basically grades or gives a value that describes how good a specific state is. And now what this basically does is it helps us calculate what we call an advantage. So before we were calculating the return, right? Let me change the color. Before we were calculating a return, which was the kind of from a step, the estimated reward towards the whole thing, which could only be calculated after a whole training episode. Now we're training something that we call the advantage. Now the advantage is basically kind of equivalent to this formula, which I'm going to explain now. And so what this is basically this QSA basically tells us that given this state and the action that we took, what is the value of kind of our environment, right? And then this is the value that the critic approximates. And what we do with that is we subtract them, so we calculate the difference between them. And the difference between them is either positive or negative, right? And what this results in for our advantage, what our advantage basically is, and what this equation basically tells us is, on average, how good an action taken at a specific step is versus the average. And so this is, you could kind of see this as the average, what we calculate as the average like value when a step is taken or when an action is taken in this state. And this is the critic's approximation of it. We find the difference between it. And let's say if this is like positive, like 3 or something, now we know to push the gradients and to push the weights of our policy model closer in this direction, right? And to try to raise the probability of this action being taken. And then if it's like a negative value, we lower it. And these two kind of play off of each other, right? The policy creates an action, and we basically see the advantage that that action gives given this equation right here. But there are a couple problems with this way of approaching things, mostly being that nothing stops. Like, for example, let's say the advantage is huge here. Let's just consider the 3, right? Nothing changes or nothing stops the policy from upgrading too much in one update. And what that problem essentially means, and the reason why that even is a problem, is because you have to remember, in reinforcement learning, different from supervised learning, the data that is generated, or the data that we have, is generated by the policy itself, interacting with the environment. So in a way, the quality of a model directly influences the quality of the data that we obtain, because obviously the model takes the action, which gets some reward, and then we use those rewards and whatever in some capacity, right, to grade that model's output and then improve the model off that. If the policy changes too much in one update, we might reach this situation where the policy becomes overly negative. For example, it becomes too bad. And now the quality of the data that we're generating is just horrendous in each and every step. And then there's no real way of going back from that other than restarting training from that step, right? And so we have to find a way to clip this policy from not improving or not changing too wildly, right? So if you can imagine, we kind of put like a little like clip on how much this could improve from the old policy, so that we don't have these huge changes. In a way, you could kind of think about it like having a learning rate that's too high. You tend to miss local minimums a lot more often if you have a really, really high and crazy learning rate. Also, this is another instance where we have where we experience something exactly once, just grade it and throw it away. Now, there are more efficient ways to go about that. And that's where we introduce PPO. And I'm going to go over the PPO paper, which is right here. Now, the paper that introduced proximal policy optimization was by OpenAI in 2017. And it goes over the equations and the necessary things that you have to know about PPO. So here, there's just an introduction. Let's read the abstract, in which OpenAI proposes a family of policy gradient methods for reinforcement learning, which alternate between sampling data. Like I said, you have to sample data through interaction with the environment. So you're generally kind of generating your own data. And then you optimize a surrogate objective function using gradient ascent. When they mention the surrogate, what it means is, in general, in reinforcement learning, the goal is to increase the reward. But as you know, in neural networks and in deep learning, our goal is to decrease the loss. And so we have to find a way to chain a reward value to a loss that we can use to then backpropagate and update our neural network. Here, they say when standard gradient perform one gradient update per data sample, we propose a new objective function that enables multiple epochs of mini-batch updates, and they call them PPO. Much simpler to implement in general. If we skip a little bit of this introduction, it kind of just goes into policy gradient algorithms. Here, like what we talked about, policy gradient methods compute an estimator of the policy gradient, and then they, for example, they find the log probability distribution in which a policy generates an action given a specific state. They multiply. Here we have the advantage, right? In the case of reinforce, it's kind of just the whole raw return. And like I already mentioned, that has a problem. And then this paper builds upon what they call trust region methods. But I'll explain all of this through this section right here, which is the clipped surrogate objective, which is what we talked about. If we can put a little cap on how much the model can improve, that can help stabilize training a lot more. And let's kind of break this math through, right? So here what they introduce, the clipped surrogate objective, they have an RT with theta. This theta is the parameters of the model. Now this RT stands for, it's just like a ratio. This ratio, you can see here, remember, the pi theta is the policy model. In this case, or in Actor-Critic, is what we kind of call the actor. And what this math intuitively shows is what we want is some ratio that the old policy, so the policy with the old weights and the old parameters, whatever that outputs, right? We also have it over the new, or we have it under the new policy. In the case where they are both old, it says R of the old parameters is equal to 1 is because we are dividing by the same parameters that's equal to 1. But the whole point of this is we kind of see like the ratio. So let's say this outputs, I don't know, this outputs like 9 or something. And then the old one would output 3. Then the ratio is 3. This new model is 3 times more potent and has changed its weights 3 times as much as the old one. And our goal is to kind of keep this ratio to a sane level. And TRPO, the trust region policy optimization, it maximizes the surrogate objective of here LCPI. Just keep the subscript as that name. We have this ratio times some advantage, which is just equal to this. But what they introduce in this paper is this clipped ratio loss, in which we take the minimum of either, the old ratio formula, or we clip it where we have the ratio formula in a range of 1 minus epsilon and 1 plus epsilon. What that basically means here is we take the difference in the policy, right? Let's take this 9 over 3 again. What we only compute is the minimum between this and a clipped version of this objective. So now we have the ratio 3, and what we have is if 3 is between a range of 1 minus epsilon and 1 plus epsilon, or if 3 is not in that range, we just clip it and we take just here in this case, it would be the 1 plus epsilon. We just take this value. Whatever's smaller between that and this is what we use. Again, the reason for this is we want to basically put a cap on how much the policy can improve per gradient update so that it doesn't overly extend and then cause issues into the future. Now, this is more clearly said here. The motivation for this objective is as follows. The first term inside the min is literally LCPI. So as you can see, this is literally this value right here. The second term, which is this clipped value, we modify the probability ratio and we don't let it leave this interval, which is what we have here. And then we take the minimum of that. So in a way, we're taking like the lower bound. We want to be as safe as possible with these updates and be as stable as possible with these updates. And that leads to more stable and generalized performance. And so here they show this in both cases where the advantage is positive, which means that this action was greater than average, and where the advantage is negative, which means that this action was less than average, worse than average. You see the little clip in the performance and how it is. And so you can have a ratio up to only this amount. This is literally like a hard limit. And the mathematics proves it. The mathematics basically sets the tone for this, in which if this number is overboard, we pick, whatever it was bounded by. Else, we just use what was generated here. Now, they also introduced this, but this showed to not be this showed to not have as many improvements as the clipped surrogate objective did. But we will go more into this when we talk about the RLHF aspects of PPO. But the way this algorithm works, and one thing we have to talk about is GAE, which is the generalized advantage estimation. This is basically like a weighted sum of the deltas. What a delta is this part right here. I'll break this down. ST equals RT plus gamma This is very similar to what I showed above for the Actor-Critic and how the advantage is computed. The delta at time t is the reward at that time step plus the gamma. If you remember the gamma from reinforce, this is basically our discount factor into the future. So we multiply that discount factor to the value in the next state. You can think of it as value next, and we subtract it from the current value. Value cur. And so what we do is we add recursively, the delta at time step t, the delta at the next time step, all the way to the delta at the last step. And we multiply it by this thing called lambda, or this lambda notation. This lambda notation is only used in GAE, and it basically controls a trade-off. You'll see down here, I believe, no. And when they talk about their hyperparameters, their GAE parameter, lambda, is at 0.95. This basically controls a variance bias like trade-off in the generation of the advantage. But how this algorithm works is we do for multiple iterations, as it's saying here, as what we see here. We have for multiple actors. What this basically means, you might think there's multiple models, but basically this is just multiple rollouts. And I'll explain more what that is. What we do is we run the policy, the old policy in an environment for T time steps. You're going to realize we're not talking in episodes anymore. We're just talking in a fixed amount of time steps. That's something different PPO does. It doesn't generate a whole episode. What it does is it rolls out up to maybe in 500 time steps, it goes to 128, for example. Computes the data from those 128 time steps. And then with that, then this is the actor part of it, right? This part, the advantage part, this is the critic part. And when we do that for a specific rollout, the reason we have so many actors here, that's a batch. Here they're, you saw that they talked about batches. Here we optimize the surrogate loss with respect to our theta parameters within k epochs and obviously the mini batch size. And we update those parameters. This is basically saying this. What PPO is basically doing is it's collecting data, right? It's like what they call buffer, right? It's a buffer of experience. And so this is where we just straight up roll it out. We don't do an update in every step like we do in Actor-Critic, which collects and then updates at the same time. Here we collect a lot of data, and then we learn from it multiple times. Those multiple times is these epochs. Now we have, I don't know, in 128 or in 500 time steps, we roll out 128. This, contains the rewards, all that, the observations, everything. With that data, we compute what we have to compute, right? Multiple times. If you know in supervised learning, one epoch means one whole run through the data set. And so what we do here is we update, and we basically do this same function, but for multiple epochs, a small amount, maybe 3 or 4, within this data that we collected. And we learn from it multiple times. So in a way, you could see it as we do a step, or actually even better, let me show you the way Actor-Critic does it so you can envision the differences. So Actor-Critic, what it does is it takes a step, then it updates. Takes a step with the new policy, then it updates. What PPO does is we generate a bunch of steps. And then from there, we update multiple times. So here we have a rollout, what we call a rollout of n steps. This is how we're going to code it up. And then here we train the epochs for k. We train for k epochs. And that is basically PPO. We're going to see it in code. You guys can go over the actual experiments that they did. They tested out clipping, or sorry, no clipping, and then the KO penalty. There is, there's a lot you can find here about what improvements were done compared to Actor-Critic, what improvements were done compared to Reinforce, and things like that. But in conclusion, they introduced PPO, which is a family of policy optimization methods that use multiple epochs of weight updating to perform each policy update, which gives stability, like we talked about with the clipping, gives stability, but it allows more training to be done in parallel and things like that. And this policy is central to RLHF. I'll do another paper reading for Instruct GPT, which is like a foundational paper and a big paper in how ChatGPT was post-trained. And we'll talk about the differences between this vanilla PPO and then RLHF PPO. But next video, what we're going to do is implement this algorithm in JAX. The implementation will include the advantage estimates. It would include the rollouts, and you get to see it live how it happens. But overall, thank you guys so much for watching today, and I'll see you guys in the next one.